Good morning. We are very glad to have Riyadh Baghdadi. He's assistant professor from NYU Abu Dhabi and also an affiliated researcher at MIT in Boston. Riyadh Baghdadi works on the intersection of machine learning and compilers, and this talk is entitled Compilers for ML and ML for Compilers. Riyadh, thank you again.
Thank you. Yeah. Thank you and welcome everybody. So I got inspired by the title of the next talk, AI for Physics and Physics for AI. So I changed my title. So it's basically the intersection between machine learning and compilers. How can we build compilers that can accelerate machine learning workloads? And how can we use machine learning to make compilers accelerate code better and make it run faster? So my main area of research is compilers, and we use machine learning as a tool. So one of the main goals in our area is to build compilers that can automatically optimize code. So the goal here is to build a compiler that takes high-level code and then automatically optimize it to generate very efficient code for different hardware targets, CPUs, GPUs, different hardware. And this is important because there are many compute-intensive areas. You look at deep learning, you look at image processing, scientific computing. All of these areas have a lot of compute-intensive workloads. And accelerating computations in these areas has a huge impact on the actual problems that they try to solve. So if we look at deep learning, for example, this is graph that shows the amount of computing need or the increasing need in computing power to train different neural networks. And if you look at this graph, training something like AlphaGo 0 requires orders of magnitude more computing power than training something like AlexNet, which was created in 2011, 2012 timeframe. And while you can train AlexNet on single GPU, you need cluster of GPUs or cluster of TPUs to train more recent techniques. And this trend just continues to grow. If you look at something like GPT-3, it's estimated that to train GPT-3, you will need something in the range of 4,000 GPUs that will run for 1 month. That's a huge amount of computing power. And the cost would be something in the range of hundreds of thousands to millions of dollars. Can you guys hear me? Or even more? Okay. One estimate I saw is $4.6 million. So that's a huge amount of money. And this is to do just one training. And as you know, if you want to develop a model, you have to try a lot of combinations, and it's just, the cost becomes crazy. And if you look at the carbon footprint for developing these models, this is a paper that showed that if you want to develop a transformer that has, let's say, something in the range of 200 million parameters, and you try different combinations, the amount of carbon that you would spend is 5 times more than what a car would produce in all of its lifetime. So it's a huge amount of carbon. So clearly training these models requires a huge amount of resources, is very time consuming, has a high cost, and has a high carbon footprint. And one way to solve this problem is to accelerate the training and accelerate the inference of these models. And there are many ways to accelerate these models. One way is to do what we call code optimizations. So what do I mean by that? I mean applying code transformations so that you can make the model run faster. And the term optimization here is different from the optimization term used in machine learning. So basically here, optimization means you change the code so you make it run faster. So for example, you change the order of loops to make them run faster. There are people that work on, you can also work on improving the model, basically changing the architecture of the model, or even designing better optimization algorithms at the machine learning level.
So you've just mentioned something about CO2 consumption and electricity consumption. Does code running faster necessarily means lower CO2? I mean, if I run very slow because my GPU is not doing anything, I'm not using any CO2. No.
So the idea is that if you run faster, you will consume less energy. It's not always the case, but in most cases, if you run faster, if your workload takes, let's say, 1 day, it will consume some amount of energy. If your workload will take just 1 minute, it will consume less. but this is not always the case, but in many cases it is the case. So the idea is, let's reduce the execution time of these models, because whenever they are running, they are actually consuming a lot of power. But there are many ways of solving this problem. So reducing the time is not the only way, but it's one way, one plausible way. And then you can work on improving the model, but also you can work on improving the hardware itself. And there are hundreds of startups that are designing specific hardware for accelerating deep learning. So our focus of the main talk will be about code optimizations. So let me show you an example for what do we mean by code optimizations. This is a concrete example of an optimization known as operator fusion. And the idea here is that, let's take this example of function written in TensorFlow. So in this function, the input, you have 3 inputs, x, y, z. And then this function is going to calculate the element-wise product of y and z, and then add the result with x, and then perform a reduction. It's some operation that you do. So if you run this in TensorFlow, TensorFlow will create the following computation graph where you have the blue circles are the operations, and then these gray blocks are the intermediate results. So it would first calculate y times z, store the intermediate result in T1, and then sum that with x, and then store the intermediate result in T2, and so on. So one way to optimize this code is to fuse these blue kernels into one single big loop. And the advantage here is that instead of accessing global memory many times to store these intermediate arrays, T1 and T2, you would just calculate things and then store them in registers and then consume from registers, and that would be way faster than actually accessing memory. And if you apply this optimization, you get speed up of 46% in something like ResNet and almost 90% in something like XLNet. So it's an optimization that you can apply. It doesn't change anything in the accuracy. It doesn't change. It preserves the semantic of all your work, but you get reasonable speedups.
Does it use more memory?
So overall, it accelerates. So you would use registers more, but that's fine. At the end of the day, your code will be faster.
So you need more RAM?
No, not necessarily. Not necessarily, yeah. Actually, you use less RAM. Sometimes if we don't have enough memory, we apply this optimization because then you avoid storing these huge intermediate arrays, especially in tensor operations. Yep. No. So all of these transformations, at least what I'm presenting now, they preserve the semantics of your original code. This is not specific to machine learning. You can apply it to any type of code. And the idea is to preserve the semantics. So to preserve the original, whatever input you give, you will always get the same output, whether the code is optimized or not.
What's the reason for having the forced
Yes. So the reason is that, so you might ask, so let me say something before that. So currently, if you need to do this, you have to do it manually. So you have to manually write this kernel and really optimize it, and that would take a huge amount of time. And you might ask then, why not the compiler would do it automatically, or why not, why doesn't TensorFlow or Python do it? And the reason is that behind the scene, TensorFlow is using libraries. So it only has these operations implemented in libraries, and it doesn't have this particular operation implemented in library. So it doesn't know how to basically map it to library. And the problem, you might say, okay, then let's just implement this operation in library. Then my answer would be, well, you can have very large number of possible combinations of expressions. And it's just impossible to implement every possible expression in library, right? So we have some expressions, some common expressions that are implemented, have very efficient library implementations, but you have huge other number of possible expressions that are not optimized in libraries. This is why someone like Elon Musk tweeted some time ago. He said, he's talking about Tesla, people at Tesla. He said, our neural network is initially written in Python, in some framework like PyTorch or TensorFlow, for rapid iteration. Then it's converted to C++, C, and raw metal driver code for speed. So they have a team of engineers that first write their model in PyTorch or TensorFlow. And then once they figure out what's the model, there is another team that take that model and rewrite it in C++ to make it run really, really faster. And what they do, they actually do those optimizations that I showed in the previous slide. But this is not easy to do. It requires a lot of expertise. It's optimizing code to really get the best performance is something that is really, really very hard. It's very time consuming. Whenever you change the model, you have to rechange your optimizations. And you get a lot of errors, a lot of bugs, so it's not easy. What we want to do, we want to use compilers to solve this problem. We want you to be able to write your model or your code, whatever code it is, and then the compiler will automatically optimize it and do all that work for you and generate an optimized code for you. And this is kind of the final goal, as I said. And this would allow more productivity, more portability, because then you would write one code and be able to target all of these hardware architectures from the same code, and it will give you better performance. And this problem is not specific to machine learning. It's something general for all compute-intensive areas. And that's why actually half of our projects are on HPC projects, where we work with people from physics, from chemistry, to accelerate their code, and the other half is machine learning. But you might say, then why don't we have these automatic compiler optimizations if they are going to help a lot? The problem is that designing these compilers is a very hard problem. And let me show you one example why. So if you look at the example of matrix multiplication, this is very widely used type of algorithm computation. The algorithm is very simple. It's one line of code. But in order for the compiler to optimize it, it has to generate this very complex code that you see here. And in order to do that, it has to apply many complex code optimizations. It needs to make sure that they are applied correctly and they are composed correctly because you have many of them. And then the biggest challenge is that the compiler has a list of many optimizations, and it needs to choose the right subset or the right combination of those optimizations. And making that choice is one of the hardest challenges that need to be solved. Why is it challenging? Because just you have millions and millions of possible combinations. The search space is very large. I will talk in more detail about this later, but just to give you an idea now. And then predicting the performance of each optimization by itself is hard. So if you go to an expert, you show them code and you say, I have this optimization. Do you think if I apply it, the code will be faster or slower? Sometimes they will not give you the right answer, just because it's hard even for human expert to predict whether a given optimization helps or not. And then there are complex interactions between these optimizations. Sometimes you apply one optimization, you get slower code, you apply the next one, you get faster code. So there are complex interactions. So how do we approach this problem? How do we address this problem? So our approach to address this problem is to divide it into two steps. And the idea of the first step is to design a compiler. Let's design a compiler that if you give it code and you give the compiler the list of optimizations that you want to apply, the compiler will succeed in applying them and generate correct code. So at this stage, the compiler doesn't automatically figure out what are the optimizations that need to be applied. It just, you say, this is the code, I want you to apply this and that and this and that optimizations, go ahead and apply them and change the code and generate me the optimized final code. So that's step one. So here the input is an algorithm and list of code optimizations specified by the user. And then the output is an optimized code. And this by itself is challenging because the compiler needs to support a lot of optimizations in order for you really to get good performance. And then the second step is to automate the selection of those optimizations. So basically design a module that will figure out now, given code, what are the optimizations that need to be applied for that specific code. So basically automate the selection of optimizations. And so during this talk, and this is challenging because in order to automate that, you need some cost model to allow the compiler to compare between different optimizations, and designing such cost models has been hard in the last 30 years or 20 years. So throughout the talk, I will address kind of these two steps. So first, I will talk about one of the works that we have done, which is Tiramisu compiler. It's a compiler designed for machine learning, image processing, tensor computations. And then I will, in the second part, I will show how we are using deep learning to automate code optimizations and allow the automatic selection of optimizations. So let's start with the Tiramisu compiler. So Tiramisu is a compiler for expressing algorithms and code optimizations. So you have some C++ API that would allow you to express the algorithm that you want to optimize, and then to specify how you want to optimize it. And it's designed mainly for code that has loops and that manipulate arrays. So it's not something that you would use for, let's say, optimizing code that has lists and trees and irregular data structures. It's mostly for tensor operations. And it relies on two ideas. The first idea is this idea of separating algorithms from code optimizations that I will explain in the next slide. And the second one is that it uses something called the polyhedral model, which is a mathematical model that we use to model code, model the code transformations and reason about the correctness of these transformations. So I will not talk about the polyhedral model, the mathematical kind of background, but I will talk a little bit about the first one. So what do we mean by separating algorithm from code optimizations? So as a user, when you write your code, you will first write the pure algorithm, the unoptimized algorithm. For example, if you want to express something like this loop where you have for x, for y, and then you are writing 0 in the array out xy, you would express it in Tiramisu like this. First, you will declare the loop iterators, x and y, x between 0 and n, y between 0 and n, and then you will specify the computation. But here, as you see, we are not specifying in which order we are storing these values, like in which order that storage is being done. So we are just saying we want to store 0 in this kind of computation or array, if you want to say. And then in the second part of your code, you specify how you want to optimize this code. And basically, by doing this, you specify in which order computations are done. So for example, you can say, I want to run this code in parallel. You just say out.parallelize x. That means you would run this loop, different iterations of this loop, you will run them in parallel. And then you can say out.vectorize y. That means you will vectorize different iterations of the while loop. So you will specify how you want to optimize code using this API. And you have different optimizations, and for each optimization, you have an API call. This is how you would optimize matrix multiplication. So first, you would write the pure algorithm. And at this stage, you don't specify how it's going to be optimized. And in the second part, you specify how you want this code to be optimized. You say, I want to parallelize the code. I want to apply another optimization known as tiling, which kind of makes the execution run in blocks. And then you want to do something like vectorization and rolling. These are all just code optimizations. But the advantage here is that someone who knows these optimizations can easily write these use this API to specify what they want. And then this would be the input to Tiramisu compiler, and Tiramisu will automatically generate this code for you. So we applied Tiramisu. We collaborate with theoretical physics team at MIT. They work in the area of quantum chromodynamics. And they had this simulation that they need to do. It's tensor contraction. So they wanted to accelerate this code. They implemented this code in C. And it was a little bit slow for them. So they came to us and said, hey, we want to accelerate this. So we used Tiramisu to accelerate that code. We rewrote this in Tiramisu. And then we applied our code optimizations. And if you would write this code in C, you would get something in the range of 1,000 statements, mostly loops. And some of the loops have up to 13 loop levels, so they are very deep loop levels. And the tensors, some of them have up to 10 tensor dimensions. So they're quite big tensors. And if we optimize this for single core, we got 10x. Then we added parallelism to optimize it for multi-core machine. We got 200x. And then we optimized this further for GPU. We got 500x on single GPU. And you can do all of these just by changing those scheduling comments or those optimization comments. So you have the algorithm is the same, whatever your computation is, And then if you want to optimize it for different hardware, you just change those API calls because different hardware require different optimization techniques. So that's one of the advantages, is being able to kind of quickly port your code to different architectures just by changing that scheduling comment or those optimization comments. Yes.
If the algorithm knows by itself the optimization that it will do, or
So at this stage, you specify, as a user, you specify how the code should be optimized.
Because
Yep.
you need to know this about the architecture and
Yes.
how to now.
Yep. So to optimize this Baryon building block code, I spent like 2 months just figuring out optimizations. And at Google, they use another language called Halide, which is very similar. So Tiramisu is kind of another version of Halide. So at Google, they use Halide, which is language for image processing. They actually use it in production, and it relies on the same idea. And they have very large number of users of that language. They actually write the code, the algorithm, but they had only 2 experts that can optimize the code. So everyone writes the algorithms and then send the algorithms to those 2 experts to optimize it. So this optimization is not easy. It requires some expertise.
So yeah, the data type, I mean, you don't specify what A, B, and C, I mean, they're flow 32, 64, what.
Yeah, in this case, yeah.
So here, like.
Yes, in this case, data type is by default int 32. But if you want to specify, if you want something else, you can specify the data type. So you can say, I want to float double or. Yep.
So on the previous slide, when you showed some optimization to the single core 24 core. When you go from single core to 24 core, I guess you can reuse a lot of things that were done in single core.
Yes.
When you go to GPU, you have to rewrite everything from scratch because the optimization should be
Not rewrite everything from scratch, but a big chunk of what you have of your optimizations will be different. Yeah. Yeah.
So in this work, is the translation to Tiramisu code needed or only?
Yes, we had to implement this in Tiramisu first, because the physics guys, they had their own implementation written in C. So we had to write it in C, in Tiramisu ourselves. And then we did the optimizations in Tiramisu. Yeah. So there's this bottleneck of you need to write the code. But usually usually people are interested in optimizing small chunk of code, not small like kernel. But if you have like a huge 1 million lines of code, then I don't think this is the right tool to do that.
And this Tiramisu translation is not for us.
Yeah, currently it's not. Yeah.
How many code optimizations roughly do you need? Like, is it that one optimization gives you a big improvement and then the others are more like marginal, or it's like how many code optimizations essentially are you doing?
Yeah, so in this particular one, I don't remember. So there are dominant optimizations that if you apply, you get kind of 80% of the speed up or 70%. And then the remaining 30% or 20%, you have to do a lot of small optimizations to really get to them. Like parallelizing code is the more cores you have, simply the more speed up you get. Vectorizing is good. Anything that improves locality, like fusing loops. If you have sequence of loops, you transform them into single loop that improves locality. So that gives you a lot. And then there are a lot of other small optimizations that.
So in this 2 months, what you mentioned, like most of it was spending on this 20 or 30%, right?
Yes, yeah, exactly. Basically figuring out what you need to do, because sometimes like you think that part of it was even like working on Tiramisu itself, because some of the optimizations were not well supported. So it's not 100% just figuring out the optimizations. But yes, I think the biggest chunk is on that 30%.
Why you don't let the algorithm to choose the best course of optimization? Because if you are doing machine learning, you can like at the end it's like matrix multiplications and matrix vector multiplications, and you can like try this in many different architectures, and at the end you can just let the algorithm choose one depending on the architecture.
Yep. So that's what I will present in the second part of the talk. But the problem there is that the search space, the possible combinations of optimizations is huge. You have 10 to the power of 150 possible combinations for a given code. Let's say that has 100 statements. And so if you pick every choice and then try it, you'll never finish. Sorry. So you need some models. You need.
Try on the configurations. Maybe you can just do machine learning and tests and predict the best optimization choice. We tried doing this with the API communications and
yes. Good speed. Okay. Actually, that's what I will present in the second part. So, yes.
Have you compared this against like keeping the code and optimize at the compiler step, the compilation step, like automatic optimization application?
So currently, we are not still able to optimize this code just because it's gigantic, it's so big, so big. So we don't do automatic optimization. But I will show at the end of the presentation, like comparison between what you get manually, like what you get with automatic techniques and what you get with, let's say, ideal.
I thought that was classical.
Classical compiler. So that C code, yes, yeah. That C code written by the physics team was written in C and optimized using GCC and like classical C compilers, -03 and.
So the comparisons you are showing
with that one is with the optimized C code. Yeah. So this is another example of accelerating deep learning models. So this is a comparison where we took a bunch of models, VGG, ResNet, Seek2Seek, and so on, and where we compared between the original model, these are the blue bars, that's the baseline, the original model, and the red bar is the model fused using Tiramisu, basically applying an optimization called fusion, where you have two layers, you fuse them into a single layer. Let's say you have conv and relu, you fuse them into conv relu layer. And these are speedups, so higher is better. And these are speedups that you get if you just apply this optimization. If you just, let's say you take, I don't know, you take ResNet and you just fuse some of the layers, you get like something around 50% acceleration, which is reasonable. You don't lose any accuracy, you don't lose anything. So there's also work about exploiting sparsity in neural networks. So what do we mean by sparsity? We mean the existence of zeros in the weight tensors. So if you have a model like this, in many cases, you can remove a lot of weights and just make them zero. And your model will keep the same accuracy. And sometimes it becomes even more accurate because it will overfit less. And there are some papers that show that you can reduce weights by orders of magnitude if you apply techniques known as pruning. In this paper from colleagues from MIT, they showed that you can, and if you apply this pruning technique to ResNet, you reduce 80% of the weights. You end up with just 20% of the weights. So 80% of the weights can be useless. In the case of VGG, you end up with only 2% after pruning. So 98% can be turned to zero. You don't need them. So we exploited, and they show that you can do that without loss accuracy. In this case, they don't have guarantees. They don't have theoretical guarantees that you don't lose accuracy, but experimentally, they show that after pruning, technically, like experimentally, you don't lose accuracy. And with those by supporting the sparsity, we could get things like more than 2x speedup in models such as Seek2Seek. Maybe in VGG, you get 50% speedup. But here, there is trade-off. You get some speedup, but you might lose in accuracy. So you have to choose. So Tiramisu is an open source compiler. You can check it and download it. We have active integration now in PyTorch, and it's actually used in production by in USQCD package. This is used by the theoretical physicist. Now, let me talk about the second part, which is now automating the search for optimizations in compilers using deep learning. So the heart of this problem of automatic optimization is what we call optimization selection. So what's optimization selection? Our goal is to develop some module in the compiler that takes the code, and then it has a list of possible optimizations that the compiler has. So we are interested in high-level optimizations. These are mostly loop optimizations, basically changing the order of loops, fusing loops. So these are the optimizations that the compiler supports. And then this optimization selection will select a subset of these optimizations or combination of these optimizations that will give you the best performance, mostly reduce execution time, minimize execution time. So one way to solve this problem is to model it as search problem. You have use search tree algorithms. Let's assume, let's take an example of a possible modelization. For example, you can, let's say we have a loop that only has one statement, and let's call it C. And then let's assume that our compiler only has two optimizations, tiling and unrolling. These are some optimizations that the compiler applies. And now the compiler needs to figure out whether it should apply tiling, whether it should apply unrolling, or whether it should apply them together, or none of them. So one way for it to explore the space is to say, should I apply tiling? And it has two choices, yes or no. And then internally, the compiler has to use some cost model to figure out whether it should apply tiling or not. And then let's say that cost model says, yes, you should apply tiling. Then the next question is, tiling is an optimization that has parameters. So the next question is, what are the parameters? And it has a lot of parameters. And again, it uses a cost model to figure out which parameters are the best. And then you do the same thing for unrolling. And as you see, you will end up with search tree with all the possible combinations. And you can use classical search techniques in this tree to kind of navigate the space, and you need some cost model to compare between the different combinations. So this problem of optimization selection can be decomposed into space exploration. And then for each point in the space, you need to evaluate that candidate. And then you evaluate it with two things. First, you do some cost estimation. You try to figure out what's the speedup. Is this good configuration or not? And then you also need to check the correctness. So these problems of, in our work, we focus on the cost estimation part, basically predicting the speedup. For space exploration, we use classical techniques such as beam search and MCTS. And then for correctness check, there are also classical techniques that guarantee if you apply sequence of optimizations, they check that the final code is correct and that you have the right to apply those optimizations. They give you the guarantees. So the goal is to build the deep learning model for speedup prediction. This model takes a piece of code, and schedule is simply list of code optimizations. So list of code optimizations. And then it predicts what's the speedup that you would get if you apply these optimizations compared to the unoptimized code. Or you can think of it as just predicting the execution time. The two are equivalent or very similar. So let's look at what are how do we represent the input of this model? So let's assume we have the following piece of code where we have for I, for j, for k, and then we have these statements. Computation in tiramisu is simply a statement. So we have statement A, statement B, and statement C. We represent this to the model as an AST, abstract syntax tree. So this is tree representation of the code. So you have, for each one of these computations of these statements, we represent them as vector operators that capture the kind of the characteristics of the statements. And then you have the loops, the loop K. We have some features that represent the loop K. And then the loop K has the two statements A and B. So these are the two statements A and B inside K. And then the loop J has the loop K, and then it has the statement C. So this is J, it has K and C, and so on. You can go. This is kind of tree. In compilers, it's known as AST. I will not go into the details of what's inside these features, but these are simple features like what are the operations that you have in the statement, like how many additions, how many multiplications do you have, and then how do you access memory, what's the list of optimizations, what are the loop bounds, things like that. And then, so that's how we represent the input to the model. And then the actual model mimics the input. The input is an AST, is 3. So we use LSTMs, that hierarchical LSTMs that just goes over that tree. So the model has 3 parts. It has this feed-forward part that takes a representation, the computation vector or representation of the statement, and creates an embedding for that statement. And then if you look at this particular example here, in this loop, this is a loop that has 2 statements. So basically, we take the vector that represents the statement C. We pass it through feed-forward model to create an embedding for C. We do the same for the other statement. And then we combine these using an LSTM. So an LSTM that goes over this and then this to create an embedding that represents that loop level and the statements inside that loop level. And we keep doing this in hierarchical way. We go over the AST. And at the end, we end up with one embedding that represents the whole code. And we use feed-forward model to predict the final speedup. Yes?
Is it the speed or the speedup? I don't understand why the speedup here.
Yes. So you have the original code, and then you have, let's say, 3 optimizations, right? Our goal is to predict how much faster this code will be if you apply these optimizations. And usually that we call that speedup. So if it's 1.5, that means it's 1.5 times faster than the original code. So you can, another way to think about this is you can predict directly the execution time. You say, I have the code, so if you predict the execution time, usually you would have to, that would be equivalent, but you would have to run this model on the original unoptimized code and then on the optimized code. And so you need to run it on both. And in this case, you just need to run it once on one, but it's not a big difference.
So the input here, is it the optimized code after you apply this optimization or before?
No, it's the original code and optimized code and the list of code optimizations. Because the thing, if you apply the optimized code, you have to actually optimize it. And that takes time in the compiler. So we remove that step and we let the model predict what's the effect of the optimizations on the code and what's the final predicted speedup. Now, the next question, now we know how we represent the input. We know an architecture. The next question is data, right, in machine learning. So the thing is we don't have a lot of programs written in Tiramisu. So how do we get data? And the answer to this question is we generated random programs. We created a random code generator that generates random programs. And then for each randomly generated program, we generate also a random combination of optimizations. For each combination, we compile them, run them, and get an execution time. So we generate a random code, then we generate random optimizations for that code. We compile it, we run it, and we get the actual speedup. And then we use this triplet of algorithm, list of optimization, and speedup as the training. This is our data point. It's the triplet algorithm, code optimization, and speedup. And we collected data set that has 28 million data points. So this data collection took 6 months on cluster that has 15 nodes. So it's very time consuming because running each data point takes between few minutes to few hours. And we need to do this millions of times. So you can expect how much time it takes. You mean after optimizing the code and? No, we know that this label, so this is for the model, this would be the input and this would be the label. We know that this label it's not the best one. It's just, yeah. It's for given code because we don't know what's the best optimization. So we cannot create a data set that has the code and list of optimizations and gives you the best optimizations. We don't have that oracle that generates that data set.
And you choose completely the optimization at random, or there is some prior knowledge about when you create this data set? Because I guess that if you
there is
uniform at random.
Yeah, it's horrible. That's horrible.
Yeah.
So there is prior knowledge. So we did that. The actual optimizations that accelerate code are just like 5% of the whole space. So if you do that, you will end up with data set that has 95% or 90% that give you slowdown, and the model will be trained to give you slowdown. So we applied some rules to prune the space and to just focus on the configurations that are more likely to give you speed up. So in our data set, I think 30% give you speed up and 70% give you slowdown using these pruning techniques. So we did this, and there is the other project that we did on halide. In that one, we use imitation learning. So you start with randomly selecting optimizations, and then use that to generate some data set that you train your model, and then you use it iteratively to generate better data and better model data, better model. I think like AlphaGo Zero does that. So this is a kind of plot of the predicted compared to the measured speed up. So in this plot, here you have a list of 5,000 randomly generated programs. For each one, you have a randomly generated optimization. And if you take one of these programs and look here, the red dot is the actual speed up, and the purple dot is the predicted speed up. So this is showing how close is and these are just speed ups. And the programs are ordered just for visualization. They are ordered based on ascending order of speed ups. So basically, if you look, you take one of these programs and look at the predicted and the measured speed up, they are quite close. So if you take one of these points, they are close to the red dots. There is correlation between what the model predicts and the actual speed up. And the mean absolute percentage error is 25% or 20.5%, sorry. Yep.
How do you verify the samples?
Yes. So the code generator itself is designed to generate correct code. So we design it so that it always generates, because then that becomes a problem by itself, just verifying that your code is correct.
Maybe after the scaling, we check that code is still the same.
We don't do that. We have guarantee that if you, so for given select set of optimizations, we check using something called dependence analysis. We check that these optimizations preserve the semantics of the code. That means they don't change the semantics, the original order. They don't change the semantics.
Yes, did you include in your dataset like maybe codes from standard libraries in C++?
No. Because the code has to be written in Tiramisu. The model takes Tiramisu code as input. So we only generated random Tiramisu code then.
So does it mean to have negative speed?
So in this case, it's slowed down. You apply an optimization and it makes your code run much slower. So this happens a lot actually.
Speed up is low.
In this case, I don't think it's negative. So negative, the speed up can be yes. So the speed up is you have the original execution time of your code, and then you have the execution time of the accelerated code. You divide the original execution by the speed up. So if your original code takes 1 day and the accelerated code takes 1 hour, then the speed up is 24. You divide that by. And now you might say 26 million or 28 million data points is a lot. Can you get good accuracy with less data? And this graph kind of answers that question. So with about 14 million data points, we get 25% mean absolute percentage error. And the whole remaining kind of 14 million data points just improve accuracy a little bit. So we are starting to see that beyond the 20, actually we see that beyond the 20 million data points, adding more data doesn't help a lot. So we need to start working on something else if we want to improve the accuracy of the model, not just adding data. Yep.
Is this evaluated on the same randomly generated data?
Yes, yeah.
This doesn't really necessarily say it's going to be accurate on real.
Yeah. Yep, I agree. Yes, the evaluation, I think, yes. It should be, yeah.
In that sense, it's not surprising, I guess.
More data, yeah.
How noisy are your ground truth labels?
They are noisy.
Like more than like 30%?
10%. We know that there's a variance, like 10%. We know that we cannot improve beyond 90%. There's always that 10%. But we know that there's this still gap of 10% that we have to bridge. So now the next question is, the next slide is the last slide, but the next question is to answer your question. Now, we know that this model works, is accurate on randomly generated data, but is it going to be accurate on real data, not randomly generated data? This is kind of comparison that answers that. So this is, here we are showing list of benchmarks. You have box blur, you have heat 2D, this is two-dimensional heat simulation. This is heat 3D. These are a bunch of, this is matrix multiplication. And then for each one, we have different input data sizes. This is mini size, small size, medium size, and so on, just to see what happens with different data sizes. And then we have here speedups compared to Pluto. Pluto is state-of-the-art compiler in our area. So we compare, we show the speedups over that. So higher than Pluto means that we are better than Pluto. And here we'll be comparing three things. So I will be showing Pluto with the red line. And then our auto scheduler, which is our tiramisu plus using the model. So basically, this is the work that I have been describing. And then our compiler, but using execution. So basically, if you want to evaluate whether an optimization is good or not, you have two choices. You can either use the model to predict the speedup, or you can compile the code and run it and get the actual ground truth. You get the actual speedup. Just one thing. And then you can do the second method, which is you compile and run and get the actual speedup. But the problem is that it's super slow. So if you do it for code, it might take an hour or two to just get the execution time. But using our model, you get it in 100 milliseconds, between 1 second and 100 milliseconds. So it's much faster than executing. So this is showing what's the perfect kind of optimizations that you can get with a perfect model. That's what this guy shows. Yeah.
Is Jarvis to take into account the architecture of you and data?
So the data that we generate is for specific architecture. So all of those optimizations will be done for that specific architecture. So if you want to change, let's say, to GPU, you have to generate a new data for GPU.
Right, or the same, all the benchmark are done in the same cluster or in the same.
All of them on the same architecture. Yeah. So one of the things that we want to do next is to see how do we generalize to other architectures. So these are the kind of the graphs that shows. So Pluto is the baseline. So that's the red bar here, the red line. And then the gray one is our work. And whenever you see that the gray bar is higher than the red bar, that means that we are getting faster. These are speedups compared to Pluto. So in most cases, we are actually getting better than state of the art. And then, but then you have to compare it also with what's the ideal speedup that we can get if we have a perfect model. And then you can start to see that there are some gaps. So this is what you would get with a perfect model. And this is what we are getting. You have the same thing like here. And in most of these cases are because the model is imprecise. So it makes some decisions that make it go in the wrong direction, whereas it should go in some other direction.
Just perfect model.
So in this case, so our model takes code, list of code optimizations, and predict what's the speed up or what's the execution time, right? So perfect model would mean what we actually do. We take the code and the optimizations, we compile the code, we run it, and get the actual execution time on the machine. Yes. The problem, if you do this, you can optimize your code using this method, but it will take days and months to be optimized because each data point in your space will take a lot of time.
So the y-axis here is percentage or?
These are speedups. So this is 2x, 4x, 6x. This is 10x. Yeah, 10 times faster.
The one blue that is faster than the green one.
Yes. This is because so there is all our auto scheduler is using the same. We are using the same search space exploration. So with the same search space exploration, if you just replace the model with perfect model, you still don't get the perfect solution, right? Because the search space has, well, let's say you use beam search or MCTS, or so the search space has problems, or the search space exploration technique. So in this case, our model makes the wrong decision, but actually that ends up being a good thing at the end. So that's.
And why the Pluto speedup is smart?
That's the baseline. So we compare everything to Pluto. We just normalize everything to Pluto so that it's easier to compare.
One question. So this is correct, because this is really answering the question about being out of distribution, but just out of interest, did you try to use this program at the bottom as training data to compare what Speedup you get against what you would have got if you were in distribution? So instead of randomly generating programs, you use this program as training data.
Well, that's a good idea. So basically you optimize your code using Pluto, and then you use that.
To lose by using this different distribution.
Yeah, I think that would be a good idea. Yeah. To basically generate data and see what happens. Yeah. Okay, so this is my last slide. So if you have any questions, please go ahead.
Okay, so we are more questions. I think most of the questions have been asked during the talk. Yeah. Thanks for the talk. Would it be better to optimize like recurrent operation, like the Scala products or any decomposition, the holistic decomposition, all those numerical algebra, like if you accelerate this, I mean, those algorithms, maybe that's count for a huge percentage in machine learning.
Yep. Yep. So you actually that's what libraries do. There's the BLICE library. There are all of these linear algebra, deep learning libraries. So they focus on the most commonly used operations or calculations, and then they accelerate them really very well. Now the problem is, what about the rest? You have, like, if we go to the physics problem that I showed earlier, like that tensor contraction. This is different type of calculation. You can use matrix multiplication to implement it, but it would be much slower. So how do you optimize these different codes that don't fit in those libraries? If all your code uses just libraries, then you should better use libraries. But what about the others? Also, all of companies like Google, Facebook, big tech companies, they are building a new hardware. And the thing is that for new hardware, you need also a new compiler, also to enable the research teams to explore new things that are not implemented in libraries. Because then if you bound them with libraries, you cannot explore new ideas. You would have just to stick with libraries, and then libraries already know the stuff that has been done with libraries. So
for this operation, maybe just like a graph. If you see it like
graph,
unlisted, the loop is just which indices. So it's a graph of which indices, and you need to find the better way to explore the graph or to make cuts in the graph or whatever. Is this what you do is equivalent to doing this on the graph of which indices where x, k, and I is are the which indices?
Yes, you can model these computations using graph algorithms, or opposite. You take graph algorithms and model them using linear algebra. But modeling them like this as dense loops gives you the fastest implementation, because our computers are really designed to do really, really well on this type of loops that manipulate arrays. Like all of the processors have been designed to excel in that case. So we try to exploit that, and yeah.
Thanks for the great talk, amazing. In this, for the large language model that you mentioned, GPT-3,
yeah,
there are this a lot of the effort is to distribute across nodes.
Yep.
With this, like what they call 3D parallelism, where they have data parallelism, high-type parallelism, and tensor parallelism. This,
yeah.
On a lot of usually, sometimes the bottleneck communication itself, but the communication between the nodes. Can you comment on that? I mean, can your compiler also take into account reducing the communication between the nodes?
Yep, actually, Tiramisu compiler does. I cannot exit, but it does distributed communication. The problem is that the people that do distributed communication by hand, the gap between the automatically generated code and that highly optimized code is quite big. So the compiler can generate distributed code, but the gap in performance is not is significant at this stage. So there's still a lot of work to be done in that area. But it's very, very important problem that has to be solved. So the idea at this stage, like this particular code is also run on distributed machine that has thousands of nodes. And the way that we do it is we optimize the code for a single core or for a single node, sorry. And then the physics team, they have their own MPI code that does the communication and just calls the single code for a single node. And we wanted to do the distributed part ourselves. But then they said, we just can't do it ourselves. It's already implemented, it's already there. So technically they don't need our distribution.
So yeah, I just want to know when does it mean the random code generation? What does the random code do? What's a random code?
Yes, it is code designed to be close to some extent to the types of code that we're interested in. So it's just you read something, you write something into an array, you read from some arrays and you write something into another array, and you have a bunch of statements like this. So we select, first you need to decide about how many loops do you have in your code randomly. For each loop, how many loop levels randomly, you select that. And then within each loop, how many statements you have. And then for each statement, how many, on the right-hand side, how many arrays you read from, for each array, how many dimensions, and things like that. And you do
generative model or something. You're not using.
We're not using that. So using generative model, the difficulty would be how to check the correctness.
But there is no correctness. It's a random code. I mean,
No, it is.
Yeah.
So it has to, okay, but let's say the generative model will generate some array, you will read. So how does it know, let's say you are reading from some array that exists or doesn't exist and things like that. So the generative model will generate some completely random code that semantically is not correct. But in our case, at least we guarantee that it's semantically correct so that it runs correctly, doesn't crash and so on. But I think using generative models is an idea, because it's a good idea that we have considered, and probably we should try think about more seriously.
I have a question. So the optimizations that you showed are at the code level. So if you want to do like at the assembly level,
Yes,
compilation, when you would say approach with automatic optimization that compiler can do with the code.
Yes. Yeah, in principle, you would be doing other type of optimizations that apply on the assembly level. So those are optimizations, because at the assembly, you lose information about loops, you lose information about arrays. It's hard to kind of reconstruct that type of information. So the types of optimizations are a little bit different, but like the same ideas should apply without an issue.
Yeah, so thank you very much for the talk. So you said you generate random code and then you generate also random optimization to get a speed up.
Yeah.
So what do you do with samples where the speed up was kind of like less than 1? So when you make things slow, what do you do with samples?
We keep them in the data set because you want the model to learn that bad case, so that if the search space exploration chooses that bad case, it should know that it's bad. So we want to keep them.
Would it be like this to swap them around and get like the target code to be the initial one and redoing the optimization at the speed up?
That's a very good idea for data augmentation. That's a good idea. I got a couple of good ideas by giving this talk. So thanks a lot.
So thanks again, Riyadh.
Thank you.